So the rest of the course will be on black hole thermodynamics. And I already explained the basic motivation when we were talking about the Bekenstein bound. So I explained that Bekenstein and his advisor Wheeler worried about what happens to the entropy when you toss a cup of tea into a black hole. So Bekenstein assigned an entropy to a black hole and proposed that the second law really applies to the generalized entropy. The ordinary entropy of matter and radiation outside of the hole plus a multiple of the area of the hole. Where, in a way I'll explain today, Hawking determined the constant in Bekenstein's formula to be 1/4. So Hawking supposedly was very skeptical and set out to disprove Bekenstein by studying the interaction of quantum fields with a black hole. But instead he ended up proving Bekenstein in a way that we'll discuss today. Now, as a preliminary, though, I'm going to explain the Kruskal-Sakaras coordinates. I imagine that's a review for most of you, and it's also more than we're going to need for today's lecture. But, well, it'll be helpful to have this picture. So we start with Schwarzschild coordinates. And we introduce a new function, r star, which is defined, its purpose is to bring this factor in the denominator into the numerator in a way you'll see in a second. So it satisfies the equation dr star dr equals 1 over 1 minus 2gm over r. So concretely, r star is r plus 2gm times the log of r over 2gm minus 1. So I think this definition is attributed to Reggie and Wheeler. And then in terms of r star, the metric is in this version, r is regarded as a function of r star. It's not a function of r star that you can write in by closed formula, but anyway, r is a smooth function of r star. And then, having gotten this far, you can follow Kruskal and Sakaras and introduce the coordinates u and v. And when you do that, you get the famous Kruskal-Sakaras form of the metric, in which you can see beyond the horizon. Oh, sorry. So this is the form which is usually assumed in drawing the Penrose diagram of the maximally extended solution. So if we draw V going this way, U going this way, so in this setup, R is a function of U and V. R is a function of u and v that we can get by inverting these formulas. So the important part is that these formulas are very complicated in the interior, but near infinity, r star is the same as r, and therefore t minus r star is what's called the retarded time in books where you read about electromagnetic radiation or scattering theory or whatever. T plus r star is approximately the same as t plus r, which is the advanced time. So this picture is for the ideal Schwarzschild solution. In a black hole that actually forms from collapse, only part of the picture is relevant. In a black hole that forms from collapse, the part that's relevant is the part that's to the right of this line, say, but I'll draw it over here. The shaded area is the part occupied by the collapsing star. The horizon is here. And future infinity is up here. So an observer who's sitting outside the star, making observations at late times, is living up here. So we're going to now we're going to think about the observations that are made by an observer who's sitting there looking at what comes out of the black hole at very late times. So I'll try to draw a picture to make that easier to see. Here's the singularity and the horizon. We won't worry too much about the matter, which is over here. But the observer is sitting here with the equipment. Okay. So time goes to infinity at this point up here. So a late time observation. Suppose for simplicity that the black hole is emitting massless radiation. And suppose we can assume that the massless radiation escapes to infinity on a geodesic at the speed of light. Then this geodesic here, it's meant to be a straight line at a pi over 2 angle to the pi over 4 from the vertical. That's meant to be an outgoing null geodesic. So at this point of the diagram, the observer receives a signal that came out on that outgoing null geodesic. Then the observer waits longer and sees a signal that came on this other null geodesic. You wait later still and see this one. The late time observations of the observer amount to observing signals that come on outgoing null geodesics from very close to the horizon. That's the key fact in Hawking's calculation. Late time observations you see signals that emerge on a null ray very near the horizon. Well, how near the horizon did a signal emerge if you observe it at a time t? Well, we could have answered that question in the original metric by solving the geodesic equation for the null geodesic. But we can, as a slight shortcut, since we've deduced the Kruskal-Sakara's form of the metric, we can observe that in that form of the metric, the null geodesics, the radial null geodesics are just lines of constant u or v. So in Kruskal-Sakara's coordinates, because of the simple form of the metric, where it's minus some function times du dv plus r squared d omega squared, so you can catch up if you're just familiar with the Kruskal-Sakara's form of the metric, which we derived, but you might know it already with any luck. So in that form of the metric, an outgoing null geodesic is just a line at fixed angles. So I'm suppressing the sphere. Or we could consider an outgoing shell, an S-wave. So it could be spread over all angles. But importantly, it's at fixed u or v. So with the way I've labeled the axes, with v increasing this way and u increasing this way, fixed u is an outgoing null geodesic. Fixed v with the incoming. So if we just look at the formula for u, that tells us, well, with, again, the way I've oriented this, u is positive to the left of the horizon, so it's negative. For this outgoing geodesic outside the horizon, u is negative. That's the minus sign of this formula. So minus u, let's let w be minus u, which is a measure of how far outside the horizon is a null geodesic. It's not a natural measure because we didn't have any precise way to normalize it. Its only properties are that w is 0 on the horizon and w prime is not 0 on the horizon. It turns out that for what I'm about to say, these are the only properties of the function w that matters. You'll actually see that in a second. The relation to w I actually think I left out a factor of r in those formulas. Oh. Sorry, is that right? Okay. Okay. I'm slightly inconsistent in my notes, but this factor isn't going to be important because the observer, we imagine, is sitting very far away at some fixed and large value of r. So whatever, this factor is just a constant. Then as time goes on, u gets closer to 0, which is what will be important. So w is this exponential factor times a constant, where the constant depends on exactly how I define w. I define w to be minus u, but I could have just as well used minus 2u. There was nothing magical about the coordinate u. You see that no matter how I define w, it vanishes exponentially as t becomes large. It vanishes as e to the minus the retarded time over 4m times a constant. Changing the constant would just shift the retarded time by a constant. There's no natural 0 of retarded time. So without knowing exactly how to set the clocks, the observer doesn't really care about what c was in this formula. So this formula tells us that if you make a late observation, you're seeing something that came from very close to the horizon, exponentially close. Now, late observation doesn't have to be very late. Suppose we have a black hole with the mass of the sun. Then 2gm is in the range of microseconds. Well, a few microseconds, I think. So if the retarded time is 1 millisecond, that would be much greater than, this 4m should be 4gm. I sometimes set g to 1. 1 microsecond would be bigger than 4gm, 1 millisecond. So if you have a star with the mass of a few solar masses that collapses to a black hole, after a couple of milliseconds, you're making late time observations. And when you're when this exponent is just 100, let's say, so 4gm was a few microseconds, but you waited a few milliseconds. So this exponent is in the hundreds or maybe thousands. So w is e to the minus 100 times some reasonable length scale. So w, after what in human terms is a very short time, is fantastically less than any reasonable length scale in physics, like the Planck scale or anything. So when you make a reasonably late observation, you're seeing a signal that came from extremely close to the horizon. Now, that is the essence of the Hawking effect, and we'll put into formulas the consequence in a moment. But let me just stop and ask if there are questions here. So, okay, I'll draw the picture I keep drawing. But now I want to emphasize that we have this pile-up of null geodesics outgoing and sending signals to the observer. The observer is living up here. Time is going toward infinity in that part of the diagram at large R. The observer is just peacefully collecting signals, whatever comes out from the black hole, which originated at earlier and earlier times. Now, whatever you're going to observe up here can, of course, be traced back using dynamical evolution, the causality of physics, to initial data on some Cauchy hypersurface. And we're going to take a Cauchy hypersurface. Well, we want to take a Cauchy hypersurface, so there was matter here. We want to take a Cauchy hypersurface that intersects all of these outgoing geodesics where they're essentially in the vacuum. So here's a Cauchy hypersurface that we'll do. All I've done is to pick a Cauchy hypersurface that intersects the outgoing null geodesics to the future of the collapsing star. So these geodesics emerged from inside the matter, but they've long since left that by the time they reach the surface S. Long since might be by a millisecond, but anyway, enough. So the observer sees a signal that arrives here, but the signal originated, the late time signal originated from initial data on the surface S. That's just a statement of causality. Anything you observe up here originated from something on the surface S. But not just from the initial data on S, but the key point is that's exponentially close to the horizon. Exponentially close means exponential in the retarded time. I remind you that the retarded time is the time that the observer infers as when the signal originated. So in scattering theory and when you're learning about electromagnetic waves or anything, retarded time is t minus r. You make an observation at a distance r in time t, but t minus r, the retarded time, is the time at which the signal was emitted if it originated from the origin. In practice, you usually have an extended object, so the signal didn't literally come from the origin, but if it was a bounded object, the signal came within a bounded distance from the origin. So up to an uncertainty of order the size of the object, the retarded time tells you the time at which the signal was emitted, as interpreted by the outside observer. So we're considering an observer. So we consider an observer where R is very large. In other words, the observer is at. But we also consider the case where T retarded is large. And that means we let the black hole settle down. Why do we look at the late time observations? Because the formation of a black hole is very complicated. A black hole might form from non-spherically symmetric collapse or very complicated initial data with normal modes of oscillation called quasi-normal modes excited initially. It takes the black hole a while to settle down. So even classically, the initial answer is not simple, and the same would be true quantum mechanically. Hawking's great insight is that if you wait till the retarded time is large, as well as the distance at which the observation is made, then you get a simple answer. The reason you get a simple answer is that what you're observing at late retarded times came from very close to the horizon. In this picture, it doesn't look closer here than here, but there's an exponential redshifting, which is contained in this formula. So this formula shows that when the retarded time is large, u is exponentially small. So the signal we get at a late retarded time came from exponentially close to the horizon. And that means that when we make observations here, we're probing the quantum state very close to the horizon. So we're probing the quantum state at very exponentially small distances. But every quantum state looks like the vacuum at exponentially small distances. So the late time observations of the observer merely probe the vacuum at short distances, irrespective of how the black hole formed. That's why we are going to get a simple answer. Any questions? So it's a general statement in quantum field theory that every state looks like the vacuum at short distances. But it's worth noting here that anyway, the important region is outside the collapsing star. So even in classical terms, we're probing a region where the state was a lot like vacuum, even before we went to very short distances. But there might be stray particles out there. And even if they are, they don't matter because we're probing at short distances. Now, the exponential relation that w, the distance outside the horizon, was the exponential of minus the retarded time up to a constant, which could be absorbed in the zero of retarded time, so it's not an interesting constant. The exponential relation also implies an exponential redshift. So if the observer is observing radiation that comes out at a fixed frequency, that radiation originated as a very high energy mode near the horizon. Now, it's tempting then to claim that a very high energy mode would simply escape along a geodesic at the speed of light. That's a little bit oversimplified, and we will correct for it later in the lecture. But if we make that slightly oversimplified assumption, we can give the quickest possible derivation of the Hawking effect. And it does capture the main idea. So I'm going to make the assumption that this very high energy signal merely streams out to infinity at the speed of light. We'll see what that implies, and then we'll slow down, back up, and correct for it a little bit. So if we have a Schwarzschild black hole, we have spherical symmetry, and we can expand in partial waves. And we actually will do that more carefully in a little while, but a simple statement we can make is that each partial wave is described by a 1 plus 1 dimensional effective field theory. Let me just call it a 1 plus 1 dimensional field theory. Okay, sorry. I should back up slightly and explain the context. So Hawking considered a free field in the background of the Schwarzschild black hole. We could consider a non-free field, but the starting point is to understand what happens for a free field. So for example, it could be a Maxwell field in the field of a Schwarzschild black hole. Although when we do an example where we explicitly make the partial wave expansion, we'll consider a scalar field, which I think Hawking did also, just because it's technically simpler. So we start with a free field in d dimensions, but when we make a partial wave expansion, we get a free field in 1 plus 1 dimensions for each partial wave. And I'm going to assume, so we'll gradually see that the qualitative results don't depend very much on what that theory is. But we're going to assume for simplicity that this is a theory. We're going to assume that it's the simplest kind of 1 plus 1 dimensional free field theory. So the very simplest with the theory of free fermions of spin a half and zero mass. So we'll see what happens in that example, and then we'll consider some other examples. And then we'll become more realistic and make a partial wave expansion of a real theory in d dimensions. However, if you've looked at the slides from a previous lecture that I posted on Canvas and sent to some of you that I knew weren't on Canvas by email, you'll see that because time was limited there, I didn't give the more realistic explanation that we will actually give today. I only gave the simplified version. So what we do is we start with correlations near the horizon. And then we just evolve them to the observer at infinity. And we'll do this first in the free streaming approximation where the field is free. Then we'll correct for that. But in the basic example of free fermions, so psi is, let's say, a positive chirality fermion, a right-moving spin 1/2 fermion. Its two-point function in the vacuum well, I want to multiply the two-point function by dw prime to the 1/2. That factor, which people wouldn't always include, I'm including it because it makes it more obvious how to make the coordinate change from w to the retarded time. So what is the vacuum expectation value of a free fermion? It's usually just written as 1 over w minus w prime, but we'll call it dw prime to the 1/2. just by multiplying each side by dw prime to the 1/2. The reason, well, okay, including this factor makes it trivial to make the change of variables from w to the retarded time. So well, sorry. So I'm going to write this in terms of an expectation value. I'm going to, I think, just write capital T as an abbreviation for retarded time. So the outcome. So what does an observer measure? Well, if you're detecting photons, the photon has an electric and a magnetic field. And the detector normally measures a quadratic function of the electric and magnetic field. You don't really have a detector that, a photon number, for example, is quadratic in the field. But you might measure the expectation value of E squared at a given time. But if you're measuring photons of a definite frequency, that means you measure electric field at time t times electric field at t prime convolved with an exponential e to the I omega t or something, or sine omega t. So in general, what the observer at infinity measures is a 2-point function, or if you were more sophisticated, a higher point function. But the basic detector will measure a 2-point function of the quantum field, in general, at 2 different times, t and t prime, perhaps convolved with a sine function or something else characteristic of whatever you're doing. So here, to make the change of variables trivial, I'll include the factor of dt prime because the fermion field has dimension 1/2. And I set these equal. On the left, I wrote down a formula for the vacuum expectation value. We were really interested in an expectation value in the actual state of the black hole. But since w and w prime were exponentially close, and also in the region outside the matter, this was effectively the same as a vacuum expectation value, which I used in writing this formula over here. As for the observer, I'm writing it as an expectation value, the average 2-point function that the observer will observe. A slight surprise is in store, and therefore we don't want to make a claim about what the observer will consider the state to be. We're just calculating the expectation value of the observer's measurement, and then we'll discuss what to say about it. So we literally get the answer by just changing variables from w to t using w equals a constant times e to the minus t over 4gm. And when you make that change of variables, you get dt prime to the 1/2 over e to the t minus t prime over 8gm minus e to the minus t prime over 8gm. Literally all I did was to replace w with t using this fact that w is a constant times e to the minus t over 4gm. You'll notice the formula is homogeneous in w, so that the constant c canceled out. And we could do it on the blackboard, but the change of variables, if you just substitute, make this change of variables, this formula will turn into this one. And now we observe that the answer is anti-periodic in imaginary time. That is, it's antiperiodic under t going to t plus 2 pi I over 4gm. I think. Yes, okay, sorry, thank you. I was in the process of detecting my formula didn't make sense, but you abbreviated that process. Thank you. Okay. If we shift t by 4gm, that would, okay. This shifts t minus t prime over 8gm to itself plus I pi. So it changes the sign of the correlation function. Sorry. Sorry. Now, for fermions, antiperiodicity in imaginary time is the hallmark of a thermal distribution. In path integrals, we'd calculate a thermal distribution with a path integral in a circle of circumference beta. The bosons would be periodic on the circle, but the fermions are antiperiodic. So this antiperiodicity means that we found a thermal two-point function at beta equals 8 pi gm. I call it beta Hawking. So the Hawking temperature is 1 over beta Hawking, which is 1 over 8 pi gm. I have to say at the moment I'm worried about a factor of 2 in that formula. But hopefully it's correct. So this is the essence of how Hawking discovered that a black hole at late time is emitting thermal radiation. So here we took the thermal radiation to be fermions that we took to be free in the 1 plus 1 dimensional sense. We could have instead assumed the simplest model with bosons. We could assume the 1 plus 1 dimensional effective theory to have a current JV that's conserved in the sense that du of JV is 0, a right-moving current. And then we would have considered JW dW let me just call the current J. We would have considered the two-point function J of W prime, dW dW prime. So in two-dimensional conformal field theory, the two-point function of a conserved current has a double pole because the current has dimension 1. And then we would find that J of t prime, dt prime, would just be the square of what we had before. Since it's the square of what we had before, it has the same periodicity, but now it's periodic rather than antiperiodic. And that, of course, is the correct answer for bosons. Bosons, a thermal correlation for bosons is periodic in imaginary time with period beta, Well, for fermions, we have anti-periodicity in imaginary time with period beta. So for both bosons and fermions, we got the correct periodicity. Now, so this is the essence of the Hawking effect, even though we're going to do it more realistically in the rest of most of the rest of the lecture, making a more realistic partial wave expansion. So now that you've seen, though, the essence of the Hawking effect, let me stop here for questions.
Sorry, beforehand when you said that we were more interested in the daytime
Yes.
radiation because it was exponentially close to the horizon. So if we were not observing that sort of thing that comes before late time, there would be like radiation that had escaped the region near the horizon?
Well, while the star is falling in, there are time-dependent fields which will cause some particle creation, and the incoming matter itself might radiate, even classically. And when the black hole forms, it doesn't form in a time-independent state. It has what are called quasi-normal modes.
I see. So this would come like some radiation from like the equivalent.
Right. So there's a transient, which in the case of a star with the mass of the sun, would be over within a millisecond or two. And the transients depend on how the star formed. They do not have a thermal interpretation. They depend on the initial state. After you wait, in the case of a black hole with the mass of the sun, for a few milliseconds, you're in the regime where we can do this calculation, except we cheated by assuming the outgoing wave was free, or that was slightly oversimplified, as we'll discuss. But essentially, this calculation is correct. And it shows that after transients die down, you will observe thermal radiation. Now, any more questions? This is an excellent time to ask questions, because this is one of the, I don't know how well I explained it, but it's one of the most important points in the course, for sure. Okay. So if there aren't questions, okay. Having gotten this far, Hawking then computed the entropy. So Hawking, yes, please.
In the regular space case,
Yes.
so temperatures 0.1 reds.
Heuristically.
But here the Hawking temperature is independent distance to the horizon.
Well, we only computed it from the point of view of an observer near infinity. So we computed the effective temperature for an observer near infinity. You might want to remember there's a redshift as radiation escapes from near the black hole. So if you tried to define a temperature closer to the horizon, it would be bigger.
I see.
Any other questions? Yes?
Since you use the pre-Fermion correlator,
Yes?
odd under W goes to minus W. So is it that any time we have a W that's exponential in time, we have some temperature that where you can use? Because all that really happened when you shift T is that W.
Yes. Okay. That's an important point that Sunil's making. So, well, I could have made that point when we wrote down the Kruskal-Sakaras metric, that time translations in Schwarzschild coordinates correspond to rescalings of u and v in Kruskal coordinates. You can see that here because shifting time by constant will shift the retarded time capital T by the same constant, and that rescales w, which was minus u. And it would have rescaled v in the opposite direction. So in this picture, okay, the reason for the relation to Rindler space is that I won't try to write the exact formula, but in Kruskal-Sakaras coordinates, the metric looks like this, and time translations act as Lorentz boosts. U to lambda u, v to lambda inverse v, which is visible in this formula. time translations rescale W, which was minus U, and they rescale V in the opposite direction to leave the metric invariant. So because time translations look like Lorentz boosts, the region near the horizon actually looks like a Rindler space with time translations interpreted as Lorentz boosts in the Rindler space. That's the reason for the relationship to Rindler space. Any other questions?
Sorry, you using the fermion to be massless?
Yes.
Was that like very important?
Well,
Because being produced
you see, if the fermion mass is small compared to the black, if the fermion-Compton wavelength is large compared to the black hole size, then the fermion gets radiated before its mass becomes important. So you only would notice the mass if it's in the asymptotic region. So actually, a better answer to your question will be clearer when we make a more realistic partial wave expansion. But for a quick answer, if the fermion mass is small, it's not very important. But if the fermion mass is large compared to the temperature, okay. I should point out that the temperature is proportional to the inverse size of the black hole. So Hawking temperature of 1 over 8 pi gm, that's of order the inverse size. So if the fermion mass is small compared to the temperature, you'd expect that it doesn't affect the radiation very much. But if it's bigger than the temperature, obviously there's going to, if the thermal interpretation is correct, there will be an exponential suppression. Any other questions? Well, at this point, we can follow Hawking and compute what the entropy must be. Well, we can really only, okay. Hawking said that dE is TdS. And for Schwarzschild, he took E equals M, and T equals T Hawking, which is 1 over 8 pi gm. So dm is 1 over 8 pi gm times ds. I really hope the factors of 2 are going to work when we do this. I think when I made my notes the other day, I wasn't careful enough. So ds is 8 pi gm dm, and that is d of 4 pi gm squared. Hawking also assumed that S equals 0 at M equals 0 when there's no black hole. So then you can integrate this formula, and S is 4 pi g m squared. Now, on the other hand, the area is 4 pi r squared. R is 2 gm. So the area is 16 pi r squared. Oh, sorry, 16 pi g squared m squared. And so the entropy comes out to be A over 4g, as I've told you a few times. It would have been unfortunate if that had come off by a factor of 2. But luckily, that was not the case. So any questions there? This is how Hawking confirmed Bekenstein and also determined that the constant is 1/4. Okay. Any more questions? Okay. So if there aren't more questions, then we're going to spend the rest of the day trying to make a more realistic calculation where we don't assume the signal merely streams outward. So, so you might ask whether it's possible in 4 dimensions to have a model where the calculation we did is actually correct. So you can, but it's a little bit strange. You have to have a magnetically charged black hole interacting with massless charged fermions. Then, the sector with lowest angular momentum in 4 dimensions, which would be angular momentum 0 if you had unit electric charge and unit Dirac magnetic charge. But anyway, whatever it is, the sector of lowest angular momentum is exactly described by the effective field theory we used. It's described by 1 plus 1 dimensional free fermions, and everything we said was correct. So there is a model in 4 dimensions, although a rather exotic one, where the calculation we did is correct. But in a more generic model, it's not completely correct. And so, as I've said a few times, we're going to do a more realistic calculation. And we will do the more realistic calculation for a scalar field phi, which will take to have mass m, although we'll carry the calculation as far as we can with general m, but we'll eventually set m to 0 or assume that m is very small. So the reason we're taking a scalar field is just that it makes the partial wave expansion simple. We could equally well do an electromagnetic field. Then we would have to use vector spherical harmonics. And I don't think we'd learn a lot more for the extra work of remembering how to do vector spherical harmonics. So we'll skip that step by using a scalar where we can use ordinary spherical harmonics that are more familiar. The action for a scalar field well, the action for a scalar field in general but now I'm going to, so actually this calculation we're going to do entirely in Schwarzschild coordinates. Actually, when I write this Schwarzschild metric, I keep doing it in 4 dimensions. In d dimensions, it has the same form with a different function here. And the precise function isn't actually very important for what we're saying, but I will write 4-dimensional formulas. So I'll write this. So then we expand phi as a sum of phi Lm times y Lms. And the effective action only depends on phi L. Only depends on L. It's independent of m by rotation invariance. And you all know essentially what's going to happen. The Laplacian on the sphere will turn into L times L plus 1. So if you work out the effective action, I'm going to just write phi L as phi. So we're going to study a particular partial wave of angular momentum L. And for such a partial wave, the effective action turns out to be the r squared came just as in, well, just as the first time you ever met partial waves, really, from the volume of the sphere, from this factor. Okay. The r squared is corrected in 4 dimensions, so I think we'll do the calculation in 4 dimensions. But there's a term that came from the angular momentum, and that term is just L times L plus 1 over 2 times phi squared. So this is our effective action for a scalar field that has the angular momentum L. But it's useful to replace r by r star, which I introduced at the beginning of the lecture, where dr star is 1 minus 2 gm over r. Then in terms of, maybe I'll call this IL for angular momentum L. In terms of r star, IL simplifies a bit. I left out the mass term here, didn't I? The mass term with the r squared m squared over 2 times phi squared. So that's the effective action in terms of T and r star. And you notice the kinetic energy is almost canonical except for a factor of r squared in front. You can get rid of that factor of r squared the same way you probably did when you learned about radiation or quantum mechanical waves or anything expanded in spherical harmonics. You just let r phi equals sigma. And then the effective action in terms of sigma has a canonical kinetic energy. So we arrive at a formula that describes not quite a free field, but a free field with a potential. Sorry, a free field perturbed by a potential. So we arrive at an effective potential. So r is a function of r star that we have a closed formula for r star of r, but not for r of r star. But the natural variable here is r star, but the potential we write in terms of r. Sorry. We should write this thing here as 1/2 times the effective potential. Because there's a 1/2 in the kinetic energy. So the potential term should have 1/2. So multiplying by 2. In other words, the equation of motion is that the Laplacian plus v effective times sigma is 0. I think with a minus sign. Now, in this formula, there are some terms that will have an obvious interpretation, and the other terms are relativistic corrections. Let me just write down the obvious terms. One obvious term is m squared. That's the bare mass. Another obvious term is minus 2gm over r times m squared. That's the Newtonian potential. This is the effect of the Newtonian potential. And there's another term that you all know. sorry. There's no 2 here because there was 1/2, so when I multiplied by 2, it went away. So there's L times L plus 1 over R squared. That's the angular momentum. So those are the 3 terms that will be familiar from non-relativistic physics. The rest are relativistic corrections.
I guess you need the sigma square in this. This all this multiplies the field square.
Yes, thank you. I wrote it as 1/2 V effective times sigma squared. And taking account of the 1/2 V effective is what I wrote here, where some 1/2s went away and one term got a 2. So the dominant terms near infinity, near r equals infinity, are the 3, which is the same as r star equals infinity, are the 3 familiar terms I wrote. But as you go toward smaller r or r star, you run into all those relativistic corrections. Now what does this potential look like? Sorry. So I deduced the potential with general M, but I think I'm going to continue the discussion for M equals 0. So for M equals 0, V effective goes to 0 at R star goes to infinity. So for M equals 0, first of all, what is V effective? It's a little simpler, 1 minus 2gm over r times L plus 1 over r squared plus 2gm over r cubed. So at large r, the dominant term is the one from the angular momentum. So, well, sorry, assuming the angular momentum is non-zero, the dominant term is the one from the angular momentum. Otherwise, we have to go to the next order, and the dominant term would be 2gm over r cubed. But either way, the potential falls off like a power at large r. And it's a sufficiently rapid power that you can think of it as a short-range potential. So this is r star equals infinity. Now we could look at r star equals minus infinity. R star equals minus infinity is the horizon. Okay. R star was r plus 2gm times the log of r over 2gm minus 1. So something I failed to emphasize is that as r goes to 2gm from above, r star goes to minus infinity. And r is exponentially small. R star only goes to infinity logarithmically, but r is of order the exponential of r star over 2gm or something, for r star going to minus infinity. So the potential vanishes very rapidly near minus infinity. And then somewhere, of course, it has a maximum. And if L is of order 1, the maximum is at r star of order gm times a few. And the height is of order 1 over gm squared. So with this potential, we can see that our wave is not completely free. A wave coming from plus infinity might be scattered back or might penetrate through the potential, and a wave coming from minus infinity could do the same. Now, our model was correct if we can ignore the potential, because the current we discussed the t derivative plus the r star derivative of phi would have the properties we assumed if the potential was 0. So our model was completely equivalent to ignoring the potential. Well, when can you ignore the potential? Obviously, you can ignore the potential for a wave whose energy is above the significantly above the maximum of the potential. And so since this is a time-independent equation, the solutions look like phi of t and r star equals e to the I omega t star times some function f omega of r star. And f omega of r star obeys a Schrodinger equation Now, if omega is large enough, then V effective minus omega squared is always negative. So the potential energy is negative, so the particle always has positive kinetic energy. So it will, with a probability exponentially close to 1, it'll propagate over the barrier. And the only thing the barrier will do, actually, is to cause a time advance. So the signal that arrives at infinity will be the same as we calculated, except it will come sooner by an amount that is frequency dependent and has to do with the time advance due to an attractive potential. Except I stated that wrong. Let me say it correctly. The potential, if omega is large enough, the potential is always negative, but it's less negative than if V effective were 0. So the signal will be delayed by the potential being less negative. It'll arrive a little bit later than we expected. But since there was an unknown origin of the time in our calculation, that isn't very important. So if the frequency is high enough that you're above the barrier, our calculation was essentially correct. However, if the energy, so what that means in practice is that if the temperature at which if you observe radiation coming from a black hole at a temperature that's well above the Hawking temperature, because the maximum of the barrier is of order the Hawking temperature squared, assuming the angular momentum is of order 1. So for frequencies much bigger than the Hawking temperature, the calculation we did before was essentially correct, up to fine details that would be hard to observe. The fine detail is just that the photon doesn't come out at the time we calculated, but since photons are coming out at all times, that's not really observable. However, for frequencies that are not much above the Hawking temperature, we can't ignore the barrier. So let's discuss what the barrier is going to do. Now, before we discuss what it does, let's try to think intuitively about what it should do. Suppose it's true that a black hole radiates at temperature T. That means it could be in thermal equilibrium with radiation at temperature T. So let's consider what happens if radiation is incident on the black hole. Well, if radiation is incident on the black hole, it might be absorbed by the black hole, or it might be scattered. Because the radiation might be scattered, the potential will reduce how much radiation the black hole absorbs. Therefore, it also has to reduce how much radiation the black hole emits by the same amount in order to maintain thermal equilibrium. So, consequently, we expect the presence of the barrier will reduce the radiation from the black hole compared to what we calculated before by a factor which should be the transmission probability. And that's the answer that we get after a little bit of discussion. The way it's heuristically described is that, sometimes heuristically described is as follows. Suppose the black hole tries to emit a photon. Well, the photon might propagate through the barrier to infinity, but the probability is less than 1. So whatever we calculated before should be reduced by the transmission probability through the barrier. And that's the correct answer. But I find that explanation of it to be not entirely convincing. I want to try to explain what I regard as a more convincing explanation. First, we look at absorption. So we look at a solution of the Schrodinger equation. So we have this Schrodinger equation, but the solution isn't unique until we fix boundary conditions. So we ask for psi omega to look like e to the minus I omega r star for r star going to plus infinity. That's meant to be an incoming wave from plus infinity. The minus sign means negative momentum, so it's coming in. And then for r star going to, but there's also a scattered wave. There's a reflected wave that comes back. Then, for r star going to minus infinity, there's a transmitted wave. The transmission probability is the absolute value of t squared. So we expect a reduction of the previous calculation by t squared. T depends on the frequency. So there will be a frequency-dependent reduction of what we calculated. It's called a gray body factor. So if omega is much above the Hawking temperature, T is very close to 1. At moderate temperatures, T is significantly less than 1. At frequencies comparable to the Hawking temperature, T is much less than 1. So actually, the picture is up here. I'm going to explain this the way it was explained, I think, by Haag and Thiering around 1988. So there was an initial value surface that we claimed the radiation was emitted from. It was somewhat arbitrary. It was just far enough in the future to be outside the matter and in the region where the black hole has settled down, but far enough in the past that the signal we observe originates at very high frequencies, short distances. Then there's a later initial value surface, S prime, where the observer lives. The observer is measuring outside the black hole at very late times, which is on a later surface in this picture. And what is the observer measuring? Well, the observer in general measures, let's say, the 2-point function of some operator. But what is the operator the observer measures? The general thing the observer might measure would be the integral dr star of some function a of r star times phi plus some other function v of r star times phi dot. However, Haag and Thiering observe that if, I think I've called it sigma though, right? Or partial wave is sigma, not phi. If sigma obeys the Klein-Gordon equation, and f obeys, and so does the function f, then you can make a conserved current from two functions that both obey Klein-Gordon. So there's a conserved charge, which is an operator O sub f, where dot means d by dt. So if f is b and f dot is minus a, then OF is equal to the integral d r star of a of r star sigma plus b of r star sigma dot. So anything you might observe that's linear in the field is OF for some solution f of the Klein-Gordon equation. Is that clear? Or can I explain something about it? It's kind of true as a tautology. Whatever you're measuring that's linear in sigma, you don't have to worry about second time derivatives because there's an equation of motion. So anything you observe that's linear in sigma is linear in sigma and sigma dot. And you can write it as the conserved charge associated to a solution f of the Klein-Gordon equation by just picking f and f dot on the surface S prime to be whatever you want, and then solving the Klein-Gordon equation with that initial data. Now, the nice thing about this is that since OF is conserved, if you want to ask, okay, we want to interpret what the observer measures at the late time S prime in terms of data at the much earlier time S. And because OF is conserved, OF on the surface S prime is equal to OF on the surface S. And to make OF on the surface S concrete, we just need to solve Klein-Gordon with some initial data. Whatever initial data we want, it's up to us. We could pick any observable at all that the observer wants to use. That corresponds to some f, and that observation would correspond to an observation of O sub f on an earlier surface. But we only expect to get a simple answer if we ask a question that involves a late observation. So let's take f corresponds to a approximately localized wave. So we want it to be an approximate plane wave. Well, in scattering theory, the very simplest would be a plane wave. But a plane wave, of course, has definite frequency, but completely non-localized in space. Completely non-localized in space would be bad for us because we want to make our observations at late retarded time, and a plane wave would mean observing at all times. So we want an approximate plane wave with frequency omega. That is approximately localized in space. So you all learned in elementary quantum mechanics how to construct such a wave. We take f to be something like, for example, integral d omega prime of e to the minus omega prime squared over 2b times e to the I omega prime r star. Well, plus or minus I omega prime r star. The observer at infinity wants to use both creation and annihilation operators. So depending, let me put in the time. Yeah, okay. I should really express this in terms of the retarded time. the observer at infinity is measuring outgoing waves, but wants to look at both creation and annihilation operators. So the outgoing waves are functions of t minus r star, but you want both signs in the exponent corresponding to creation and annihilation operators. And also I need to put a constant here, which now gives me a wave that's localized where omega is near omega prime, if b is small. Small really means much less than the Hawking temperature. And then c is large. So this wave is localized near a definite frequency and a definite value of the retarded time. Or at a given time, it's localized near a definite value of r star equivalently. So the observer, I wish I could draw a nice picture. The trouble is that that picture is not very nice for what we're talking about. A more naive picture is better. I didn't plan well to draw it, though. Okay. To find out what OF is on the initial time, the observer starts with a wave like this, a wave that's approximately localized in both position and momentum. And it's an outgoing wave, but the observer wants to know what it came from at an earlier time. So you evolve that wave backward in time. Now that's confusing, but the time reversal of the process would be less confusing. The time reversal would be scattering from the black hole. The time reverse problem, we would send a wave like this in from the far past. It's an approximate plane wave. It might be scattered or it might be absorbed. By time reversal symmetry of this problem, the same is true here. So to calculate what is the operator OF on the initial value surface, the observer starts with this approximate plane wave or the later time, evolves it backwards in time. Going backwards in time, it might be either scattered or absorbed. So I guess I should use this picture. So the observer takes the wave packet that starts up here, sends it backward in time. Scattered means it would go down this way, and absorbed means it would go down this way. The process is exactly the time reversal of ordinary scattering and absorption. So the probability, the result is that LF on the surface S is the transmission amplitude times what we assumed before, what we get if the effective potential is 0, plus a scattered wave. And that scattered wave lives near r star equals infinity on the surface S. The scattered part of the wave isn't going to do anything interesting. So the observer measures now OF. Well, you measure not literally OF, you measure correlation functions of OF times a similar OF. Probably you would take, the most obvious thing to do was to take one OF with a plus sign and one with a minus sign, so a creation and an annihilation operator. Anyway, you measure some kind of correlation functions of these operators OF, and effectively you're measuring the same operators we had in the first part of the lecture, multiplied by an amplitude t of omega. And there's another piece of what you're measuring, but it doesn't do anything interesting because it lives near infinity where the state is effectively the vacuum. So our previous computation needs to be corrected by t of omega for each operator of frequency omega. So if the observer at infinity wants to know how many photons there were of frequency omega, then that person uses a number operator of frequency omega, which means a creation operator times an annihilation operator. One will get the factor t of omega, and one will get the factor of t of absolute value, T of omega absolute value. So the probability is modified by a factor T of omega squared. Yes?
General observer measures should trace sigma prime, but I managed sigma dot actually.
Speak louder, sorry. I didn't quite hear you.
Observer measures
Oh, the observer, okay. The observer measures OF of sigma prime. Well, the observer is measuring this. But OF of S prime is actually equal to OF of S, which is a sum, assuming the retarded time was late in the construction of the function f. That's a sum of two terms. T of omega times what we got in the naive calculation at the beginning, plus R of omega times a term that doesn't really contribute.
What I mean is a linear combination of the field and time derivative, right?
Time derivatives went away because
Oh, that's
it all went into f. What?
See, because from the charge formula that you wrote down, there was
Yes.
time derivative.
This is sigma dot. Also.
Oh,
Well, let's just review where it came from. The current was f. The current was f d mu sigma. So then when we evaluate the charge, what comes in is the time derivative, which I wrote as a dot in that formula. Any other questions? Okay, if there are no more questions, I guess I should wish you all happy Thanksgiving. And we have 2 more lectures next week. I won't lecture the week after next, and the reason is that there are conferences going on here and at the Institute on matters relevant to the course, related to the course. I'm actually lecturing on Monday. I think at the PCTS it will be, I'm not sure. So you can think of that lecture as a substitute for the 2 I'm not giving for this course. But anyway, I'm mentioning the conferences because some of you, if you haven't done so already, might want to register. I imagine it's still possible. And so, see you next Tuesday, and we'll have 2 more lectures next week on more on black hole thermodynamics.